So now back to what we've discussed in the previous class, and then we'll start looking at the examples. So in the previous class, what we've done, we derived before, the class before previous one, we adopted rotational Newton's second law for a multi-particle system, right? As a result of that adoption application, all internal torques disappeared, they cancel each other out. As a result, we ended up with the rate of change of the total angular momentum of a multi-particle system. Rate of change equals to the net external torque acting on the system. Only external torques, right? And then, since we knew the amazing properties of the center of mass point, so we decided, right, what if we tried to apply the center of mass for that equation, right? Okay, so we've done, and as a result, so basically we rewrote total angular momentum and the total net external torque. So the total angular momentum sort of decomposed into two terms. The first one was sort of like an angular momentum of a fake particle with the total mass of the system positioned at the center of mass of the system, right? And so the angular momentum of that particle was calculated relative to whatever your inertial reference frame you used, right? So it's basically angular momentum of that fake particle position of the center of mass and calculated relative to the to your inertial reference frame. And of course, the second term, the second angular momentum, was sort of the total angular momentum of the system calculated relative to the center of mass. So basically, you take the first particle, linear momentum, cross that with the position vector which defines position of that particle relative to the center of mass. So you'll calculate the angular momentum of that particle relative to the center of mass, then angular momentum of the second particle relative to the center of mass, and so on and so on. If you add them up, you will end up with that net angular momentum of the whole system relative to the center of mass. So we had two terms. And then similar, we ended up with the torque, net external torque. So the first part of the torque was if you calculate the net external force acting on the system, right? Net external force acting on the system applied at the point of the center of mass, where that fake particle is. And so calculate the torque relative to your inertial reference frame. So that was the first torque. And the second torque, of course, first particle, external force acting on that particle. So calculate torque of that produced by that external torque, by the external force, all right, relative to the center of mass. Then second particle, external force acting on that particle, again calculate torque produced by that external force relative to the center of mass. So you calculate all those external torques relative to the center of mass, add them all up, and that was our second term, right? So then those two terms we plugged in that adopted rotational Newton's second law, and miraculously some terms get cancelled, and as a result, what we had at the end is just a rate of change of the total angular momentum about the center of mass and the net external torque about the center of mass, right? It looks like a rotational Newton's second law written relative to the center of mass point. And very often center of mass point is an accelerating point, which first looks like a strange, because how come that you apply rotational Newton's second law relative to an accelerating point, which sounds completely wrong. But the thing is, we're still effectively in the inertial reference frame. Just miraculously, some terms disappeared, right? Okay, so that's what we discussed in the previous class. And now let's apply that. And we started I drew only the picture, but I couldn't move much, right? So now let's start from the very beginning. So we're going to describe a falling yo-yo. Such a funny name, yo-yo, right? I actually never try to understand what's the origin. But anyway, so let's assume that we have a ceiling, massless cord wrapped around yo-yo, and the yo-yo is going down. So we need to describe that motion. Of course, you solve the problem like this, right? But now I want to apply what we've discussed here thoroughly. So first of all, yeah, probably I need to write what is given. So we have mass of the yo-yo, radius b, right? And then, of course, first of all, before we start doing anything, we need to decide which reference frame we're going to use. And of course, it must be inertial, right? Okay, so I will position my reference frame at the point of contact, or at this point, right, where the cord is attached to this ceiling. So let me position a line x-axis this way, y-axis, oh, damn it, ugly, right, y-axis, and z-axis, okay, right-handed coordinate system, the z-axis must be into the board, so that must be z-axis, right? Okay, so that's coordinate system. And after this, which equation must be used in order to describe that? So we're going to use what we introduced, right? And let me sort of summarize in this problem what we've done. So first, how did we get a translational motion, right? So we've done this step. So first of all, probably I will summarize there, and then I will start solving over there, right? So first, which way I wrote it? So first we adopted Newton's second law, adopted or applied, but I don't know, for whatever reasons I like to use adopted, right, to a multi-particle system, right? You remember, adopted to a multi-particle system. So when we've done it, so all the internal forces disappeared, right? And we ended up with the rate of change of the total linear momentum equals to the net external force acting on the system, right? So that was our first step. And then we introduced the center of mass point, right? So then we, which way I wrote it? Okay, using the center of mass. Use center of mass point, and of course we found two amazing properties, right? So the no, without a dot. So the total linear momentum can be found using the fake particle m, and which we wrote just r dot, yeah, r dot. And then of course a rate of change of the total linear momentum equals to, okay, mr dot, okay, mr double dot, right? And then, of course, as a result, this can be rewritten, of course, using mr double dot equals to f external, mr double dot equals to f external, right? So that's, and if you solve this equation, you remember, we discussed, if you solve this equation, you will get a trajectory of this fake particle with the total mass, and that's what we called the translational motion of the system, right? Some partial description of the motion of the system, right? So, you know what, I will frame it with blue, right? Okay, so that's what we need to describe this, but again, it will give us just a translational motion. And now let me write something like this, but now for rotational Newton's second law. Again, so first we adopted, you remember, okay, let me separate this. So rotational Newton's second law adopted again for multi-particle system. And of course, we ended up with what? Rate of change of the total angular momentum equals to the net external torque acting on this system. So that's what we Good. And of course, this equation and this equation must be written relative to inertial reference frames, right? Okay, I must probably emphasize on that, right? Inertial reference frame. So it must be written to inertial RF. And of course, this also relative to the inertial reference frame. And then, that's what we've done yesterday, where we applied center of mass point, right? So use Cm, center of mass, and as a result, this equation was reduced to, okay, let me make this arrow smaller. So we use center of mass. And as a result, we ended up rate of change of the angular momentum about the center. Okay, you know what? Let me write about the center of mass, not just Cm. So about Cm, about the center of mass, equals to the rate, or equals to the net external torque, again about the center of mass. Right, so net, okay, I will put upper script external, or maybe I just look at my notes and I still managed to write using subscript, and below about Cm. Right, so that's what we need. We need to use this equation and we need to use that equation in order to have a complete description of the system. You see that we need to see all the forces and we need to identify all external torques. So now let's continue. Right. So I need to show, of course, the center of this disk, right? So radius is let me show it here. Probably, yeah, let me write it here. So that's B, and all the forces, and of course external forces only. Of course, those are mg, and of course the tension. So let me show it here, T. Okay, so now, probably I will. So now we know this. So what about R? R, it's a position. It's a position vector, defines position of the center of mass point, right? So that is obviously, let me use this, it's important, right? So let's say this is my R, right? That's center of mass. So R defines position of the center of mass, right? And using that R, it's not the most convenient, right? So let me use something else. Okay, so in order to do that, let me introduce vector B. So let me put that as a sign, vector sign on top. So R that way and B from the center of the disk to the point of contact with the cord. B that way. I picked that way. It's not a big deal. You could have picked in the opposite direction, but you understand, since we will have to calculate torque, it's better to use this vector. It's slightly more convenient. And let me introduce also this vector. Let me call it y, since it's along y direction, so I decided to use y anyway. Right? So we have a triangle of vectors. Okay, let me separate this. And I can write so that R plus B equals to vector y, right? So R plus B, it's a vector y. Okay, so now, of course, I can differentiate it twice. Vector B is constant, so, of course, R double dot equals Y double dot, right? So, of course, R double dot equals to Y double dot. So I can replace that over there. Okay, so now, and of course, M capital. Yeah, I will use M small. Easier to write. But I wrote here M capital because in our derivations we used M capital, right? But of course, now I will switch. So as a result, this equation can be rewritten. Okay, I will write it here, probably underneath. So this equation m r double dot equals to f external, of course, can be rewritten as m y double dot. Okay, now since everything is in the y direction in this equation, so I will just use pluses and minuses to show directions. And every time, of course, in Newton's second law, acceleration we assume to be positive, right? Okay, so then equals to forces. Forces, mg positive and t negative, right? So it will be mg minus t. So that's our equation number one. But of course, it's not enough, because we have two unknowns, y, position of the point of contact, and tension. So we have two unknowns, one equation not enough. So let's use the second equation. All right. Yeah, so now this. So let's write down torque first. Let me start with the torque here. So torques produced by, and again, about the center of mass. So torque produced by mg, of course, will be 0. So it's a 0 cross with mg, of course, will be 0. Then plus torque produced by tension. And again, about the center of mass. So that's why I introduced vector b from the pointing from the center of mass to the point where the force T is applied, right? Because that's what R is in the definition of the torque. R cross F. R, it's a position vector which defines point where the force is applied. Right? So B defines a point of application relative to the center of mass. So that's why I introduced that vector B. So, and of course, vector B is in the negative x direction, right? So it will be plus, which way I write it? Minus B x hat, right? Crossed, I hat, which I used it. Okay, in my notes I used I hat, what a big deal, right? And of course, crossed it with vector t. T is in the negative y direction, so it will be minus t y hat, right? Okay, so, and that of course must be equal to the rate of change of the angular momentum above the center of mass. Okay, let me write it. So L, rate of change about the center of mass. So of course we can calculate cross product. X cross B is Z. So it will be B T Z hat equals to the rate of change of the angular momentum, of course, about the center of mass. And now we have to use something which we introduced at the end of the previous class. You remember I digressed a little bit in chapter 10, I think, right? And we wrote down that for the symmetrical rigid object, like in this case, it's just basically a disk. So the angular momentum can be written as the moment of inertia, right? Times angular velocity of the object, right? So we're going to use over here that L equals to I omega. And of course, moment of inertia over disk, it's a 1 over 2 m, in this case, b squared, because b is the radius. Okay, so now, should I write? No, okay, I will open up, I will write I later, right? So this is the rate of change, dot is missing. Right? So it will be, as a result, I omega dot equals to b t in the z direction. So from now on, let me, probably I will drop z direction because, okay, I know, so angular acceleration, right, is in the z direction. Omega will be also in the z direction. Yeah. Okay, so that's just I alpha equals b t z, right? And of course, as I said, now I will drop a vector. So I will end up, of course, with I alpha equals to bt. So that's equation number 2. But it looks like we made the situation even worse. We introduced a new unknown. So before we had yt, now we have also alpha t. But of course, you know, now it's time to utilize the fact that there is no slipping at the point of contact, right? So which is a very common situation. Right? So now we need to connect alpha and y. So we need to use now a small bullet. Basically, it's like equation number 3, which we need in order to link these two equations. So no slipping conditions. No slipping condition. Okay, I usually try to draw something nice on the diagram, right? So to show what that is. So let's assume, so this is at the moment of time t, right? So moment of time t, the point of contact is over here. But let's imagine that at the moment of time t equals 0, at the initial moment of time, and let's say, for example, the point of contact was at the, for example, at that point. Or if you don't like it, how to make it work mechanically, okay, you can imagine that the point of contact was there. Not a big deal. But I imagine that that was my point of contact at the initial moment of time. And of course, on the disk, the point of contact at t equals 0, let's assume was here. So this point at the initial moment of time was there. So it means that this distance must be equal to this arc length. Right? So it just means that this distance must be equal to the length, arc length of this. Right? So of course we can introduce angle. So this is theta. Right? And of course, theta dot, it's our omega, and theta double dot, it's our alpha angular velocity, angular acceleration rate. So, and of course, the no slipping condition, this distance is just y, absolute value of the vector y, which that's what we have here. And it must be equal to b times theta. Of course, theta is in radians. Right, so we can write y equals to r theta. And of course, I will emphasize so that theta dot equals omega and theta double dot equals to alpha, right? So those are connected, of course. Right, okay, so and what we need to connect alpha, alpha. Yeah, it's a theta double dot. Right. What? Yeah. So y double dot equals to r alpha. Okay, so of course alpha equals y double dot divided by r. Okay, so we can plug it. Equation number 2. So effectively it's equation number 3. So we can plug it into the into this one, right? So and of course let me also insert that moment of inertia is 1/2 mb squared. Okay, so now I can write 1/2 mb squared moment of inertia times alpha y double dot divided by r. And equals to b times t. So basically I rewrote that equation over here. So what? What is r? B, right? Damn it, it's force of habit, right? Because most of the time it's just r, and now right, in the no slipping condition, I kept using r, and you haven't started screaming at me. Right, B, and of course here, B. Yeah, I did say B, but still wrote R. Yeah, force of habits are very strong. Right. So y divided by B. Right. Okay, so of course B, this, that, the whole B gets cancelled. And from here we can get that I think I wrote t first. Yeah, t equals to my double dot divided by 2. And now plug it into the first equation. Equation number 1 into the equation number 1. So we will end up with, of course, so now equation number 1, it's my double dot equals to mg and minus tension, which we just wrote down. So my double dot divided by 2. M, mass distraction, right? M will be cancelled. Right. And as a result, we will end up, so that goes to that side, it will be 3 over 2. Okay, I will solve it immediately. So y double dot, it will be 2 over 3 g, right? Okay. Okay, so that's the acceleration, of course, of the point of contact and of the center of mass. And yeah, of course, you can easily integrate it. And of course, the second tension, second unknown tension in the core will be m over 2 to 3 over 2/3 over times g. So it will be mg over 3. Is it correct? Let me check. Yeah, mg over 3. So that's tension. And again, the major point is over here, right? That's something. Justify why we're using this relative to the point which accelerates. And this point is definitely accelerating because there are non-zero external force acting on the system. As a result, center of mass is accelerating because T and mg, they are not equal to each other. And of course, mg is stronger than tension, right? So that's why it's accelerating downward. Okay, so that's the simple example. Right. Okay, maybe not so simple, but not ridiculously complicated. So the next one. So that's, okay, the next one I used to solve, and then I decided not to. Right? But I want to discuss it in order to emphasize on one point, sort of conceptually discuss it. It's actually, this example is from the book, example 3.3, so where you have a turntable initially at rest, and then you take a piece of sticky putty, right, and you throw it at the disk. So of course it hits the disk, what can be used as a disk. I don't want to use my plates, but probably I will have to use. So the plate, right, so it hits the disk, right, and of course the disk starts spinning, right? So of course you need to, classical problem, you need to find the angular velocity of the disk after this collision, right? All right, okay, so what I want to discuss, I'm sure that you know how to solve it. Of course, you use conservation of angular momentum. First of all, why? Conservation of angular momentum can be used because the net external torque along z direction, in the vertical direction, because that's where all angular momentum is before and after the collision, right? So you need to look only at the torques in that direction. And there's only one external force which can ruin conservation of angular momentum in this case. It's for example, let's say you have an axle right over here, goes through the table, right? So friction in that axle can ruin conservation of angular momentum. That friction can produce torque in the z direction, right? And of course, the problem says, let's assume that there are no friction, right? So that you can use conservation of angular momentum. Right? And so, yeah, angular momentum is concerned, the system consists of two parts, right? The body and the table, turntable, right? And before the collision, of course, where is the whole angular momentum? Of course, the whole angular momentum is in the body. Before that, where is the origin? Of course, the most convenient point for the reference frame, for the origin of the reference frame, is at the center of the turntable, right? I think it's the most convenient. Right? And of course, you have to tell where is the reference point, because all the quantities which you use in this problem are sensitive to the position of the origin. Torque, angular momenta, right? They're all sensitive, right? So, of course, that should be mentioned immediately. Right, so before the collision, right, so the total angular momentum, which is constant, is in the body, moving, flying. The turntable doesn't contribute anything. Then, after the collision, turntable is spinning, and the body which is attached to the turntable also spinning. So now, after the collision, they both have some amount of angular momentum. So what happens? Basically, during the collision, the angular momentum, which originally was in the ball, was shared with the turntable. And you remember the role I emphasized. What is the role of the internal torques in the multi-particle system? And I told you, it allows the system to redistribute the angular momentum within the system. Again, those internal torques, they are not capable of changing the total angular momentum of the system, because that's only external torques can do. And I told you that what's the role of internal torques? That it allows to redistribute the angular momentum, send it that way or this way angular momentum, but of course the total angular momentum will be the same. And that's what happens over here. During the collision of the body with the turntable, there are here internal torques, of course, relative to the axle. That's where the origin is. So the internal torques allows us to share linear momentum. Angular momentum. First it was in the body, after it still some in the body, and some in the spinning turntable. Right. So I wanted to discuss again the role of internal torques, right? So they allow to redistribute the angular momentum. In this case, share this ball. Okay, this body shares the angular momentum with the turntable. Okay, so I wanted to discuss that. The rest, you solved this problem in Physics 1, right? So I don't feel like solving that. Although I did, and then last year I decided to skip it. Right. And another thing about this problem which we just discussed, we don't use the idea of the center of mass over here, right? Not like here. Right? So we just use these formulas. Right? So the next example. This example is from the book, but I'm not a big fan of how it was discussed in the book, so let's do it diligently. So what do we have here? A dumbbell. So basically, dumbbell consists of 2 point masses connected by a massless rigid rod. So the distance between them is fixed. So we have M, the system M&M. It's like candy, right? M&M, right? And connected with the rigid rod, massless, right? So a rigid system, but still multi-particle system, right? And so at the initial moment of time, you know what? Let me draw it, and then at the initial moment of time, somebody tapped the left mass over some period of time delta t. So the force was applied or is applied over some period of time delta t, and we will have to describe the motion of the system. Okay, so let me start cleaning and drawing. So a similar problem will be in your homework, but slightly more complicated, because in this case, a force will be applied in a y direction, but in the homework, the force will be we'll have components in the along the y and along the x directions. But it just doesn't make that ridiculously complicated, no. So example 3.4. So we have a dumbbell system. Double L, yeah. And really? Yeah. Dumbbell. So what is given? M, and the distance between them is 2b. M and M. Then, okay, yeah, picture. All right, so let me estimate the amount of space I might need. So the first mass, the second mass, they're connected with a massless rod, distance between, over distance 2b. And, yeah, mass, mm, let me show it here, mm, and the force is applied the left mass. So F, and it acts over the period of time delta t. Okay, I guess this marker will be better. So F, yeah, it is better. Huh. Delta t. So we need to describe this motion, the motion of the system, And again, the first.
Does that say 26?
Huh?
Does that say 26 between the masses?
No, that's 2b.
Oh, 2b. Okay.
Yes, no numbers, right? So we're not in physics 1. We barely have any numbers, right, except in the homework. B.
Right, makes more sense.
Yeah. Actually, yeah, it does look like 6. And then we have dumb 66 EL. 66, right?
Oh, yeah.
Okay, so we cleared that. It looks like B. Right. Oh, yeah. So now, of course, first of all, before we start describing any system, we need to introduce the reference theorem. The first thing first. And again, this is at the initial moment of time, t equals 0, right? So force acts for a period of time delta t, and then, of course, the system, we understand how the system is going to move, right? So it's going to experience motion like this. So it will experience translational motion and plus rotational motion about the center of mass. Classical description. Right. Okay, so coordinate system. I will position it at the center of mass. At the point where the center of mass is and will be at the initial moment of time. So that is t equals 0. So that's the point of the center of mass at t equals 0. Because, of course, next moment, the dumbbell will start moving. The center of mass will start moving. But I will still keep my origin over here. Right. So that's my x. And, of course, that's my y. Damn it. Slightly not straight. Right, and so now, again, usually you start with fundamental equations, which must be used in order to describe this motion. And now obviously you understand. So we're going to use translational motion, rotational motion, right? And, all right, so we have force acting on the system. So, of course, it will produce translational motion, right? So, translational motion of the center of mass. Then also, since force is applied of the origin, of the position of the center, of the origin of the reference frame. So of course there will be torque. If there is a torque, angular momentum will change, and of course we are going to experience, not we, the system is going to experience some translational motion, right? So basically we can say that first the system doesn't have any linear momentum. It is at rest, right? And then force acts through this force, some amount of linear momentum will be dumped into the system. So through this force, some linear momentum from the outside world will be dumped into the system. Right? So we will calculate that amount linear momentum, sort of that donation of the linear momentum to the system. And then we know how we can describe the total linear momentum of the system using center of mass point. So that will be the second step, right? And then the same we will do with the angular momentum, because we have force acting off the origin at a distance, some distance of the origin, so there will be non-zero net external torque. And of course, through that external torque, some amount of angular momentum will be dumped into the system, right? And again, we know how to describe that. So let's now do it diligently. Let's describe all that dumping of angular and linear momentum, right? So, and again, it's a multi-particle system, right? So we can apply all that. Right? So first, let me put the bullet, and of course, we will start with Newton's second law adopted for a multi-particle system. So it will be dB over dt equals to dF. Oh yeah, I can write external force, right? So that's the beginning, right? So that will allow us to calculate, so if we integrate it, it will allow us to calculate the amount of linear momentum donated to the system. Right? So I can rewrite it as dP from t equals 0 to delta t. Okay, linear momentum at the moment of time, delta t. Let me maybe write, P at delta t. Yeah, it will be better to write this way. And P at t equals to 0. Of course, initial linear momentum is 0. We know that. And so here, integral of f dt, right? Of course, from 0 to delta t. F is constant. Yeah, probably I should emphasize on that. F is, it's a constant force which acts over the period of time delta t. And of course, integration is trivial because of that. So of course, as a result, we will end up that amount of linear momentum given to the system, donated to the system, dumped into the system, will be equal to, I think it's a vector form, yeah. Why did I drop the vector? It's important. So F delta t. So that's the amount of linear momentum donated. Linear momentum donated to the system. So now that system has linear momentum, and from the other side, you remember the amazing properties of the center of mass. If you know the center of mass point, you can easily write down the total linear momentum of the system by using that fake particle with the total mass of the system, position at the center of mass. So let's do it. Let's use it. So let me write from the other side. From the other side. All right, so we can write that the total linear momentum of the system equals to the total mass 2m and times r dot. From the other side, okay, let me write property of a center of mass. Property of the center of mass. That first amazing feature which we introduced immediately after differentiating the definition of the center of mass. We ended up with this. It was m capital times r dot. So the total linear momentum can be found if you chase just one fake particle position at the center of mass. So now, of course, we can combine these two things and we can get the translational velocity of the center of mass, which describes translational motion of the system. So of course, as a result, so R dot will be equal, so from here it will be what, F divided by 2m, right? F delta t. F delta t divided by 2m, right? So I can frame it. I think I switched to V. Okay, let me write over here also VCM. Yeah, and of course this is still a vector, I want to keep it in a vector form. And especially it's must be kept in a vector form in your homework because you're going to have force. The force will act at the angle. So you'll have x component, or x component, y component, so you have to be careful about directions. Right, so that's the first part. And now, let me separate it. So that was the first bullet, now the second bullet. Let's do the same with using rotational Newton's second law, basically, right? Right, so L dot equals to the net external torque. And again, we will use, since the system is symmetrical, we're going to use stuff which we introduced at the end of the previous class, right? So the moment of inertia, angular velocity. But we need to carefully write this external torque. External torque, okay, I will continue. So I will frame this and continue writing down external. You know what, let me write underneath. External torque equals. So, of course, R cross F. R cross F, that's by definition, right? R cross F. And so what is R? R is that. It defines position of the point where the force is applied. So it will be B and in the negative x direction. So I can write it as minus B x hat. I don't remember I used x or, yeah, in this case used x in my notes. So and crossed it with F. F acts in the y direction, positive y direction. So it will be F y hat. Of course, in your homework, there will be here F, component of F in the x and the y direction. So, of course, torque will be different. Okay, x cross y, it's z hat, and so minus in front. So we'll have minus b f and z hat direction. And so we can go back to our equation, of course, remembering that L equals to moment of inertia times angular velocity. And of course, moment of inertia in this case, simple again relative to the center, mb squared, so it will be 2mb squared, 2mb squared omega. Yeah. Although, you know what, I slightly jumped ahead. Okay, so at this last line, I don't need it right now. But again, it's not wrong. So I'll just, first I want to calculate the amount of angular momentum dumped into the system, like over here, right? So I want to use the same approach, the same, the same method, the same approach. So I will just integrate these once in order to get that the amount of, in this case, angular momentum. So it will be integral of dl from L at t equals 0, which is 0 because initially the system was at rest, so angular momentum was 0. And of course, the angular momentum at the end of the impact, right? So again, it's a vector equals to torque is minus BF minus, yeah, started doubting myself, right? So minus BF z hat dt, yeah, and from t equals 0 to the moment of time delta t later, right? So that integral gives us the amount of angular momentum dumped into the system, right? Because of this force acted off the origin, because of that torque. So it will be L equals minus BF z hat and delta t. Right? And now, only now, I want to use this expression which I wrote over there. So of course it is equal to 2m b squared and omega. So this will allow us to find the angular velocity of the system. Angular velocity. So omega equals, so what, b gets cancelled. So it will be minus f delta t z direction divided by 2mb. Right. So let me put it like this. So that's the absolute value of the angular velocity, right, in z direction. Let's just quickly check, does it make sense? Right. Of course, we know from our everyday experience, so the system is going to spin this way in a clockwise direction, right? Clockwise direction, it gives us clockwise direction, it gives us omega omega must be xyz. Okay, let me show the z direction first. Xyz, z is that way, right? That's the direction of z, right-handed coordinate system, right? But omega is in the negative z direction, that way. So that way gives us clockwise direction. A right-hand rule, right? You remember how to connect, how to find direction of omega. Yeah, so it matches our understanding, conceptual understanding of the motion. So that's the first part. That's the second part, right? And so now we have so translational motion and rotational motion about the center of mass. And let me emphasize, so this is clockwise direction, clockwise direction. I just look at my notes, probably I should mention it. So let me check what else. And again, that's what we have at the end of the impact. And of course, since we don't have any friction, so this translational velocity will stay with the system forever and ever. And again, also that angular velocity, right? So it's at the end of the impact. Okay, great. So we can describe the system using this center of mass point. But you know what, describing of the system using just a center of mass point, it's sort of like a describing of the life of people in the country using the life of the president. So the center of mass is like a president, right, of the country. And using his life to describe our lives, it's not very accurate representation, right? So this I usually compare like life of the president, but I still cannot find analogy with this. It's sort of like a life of a people relative to the president. Still it boils in my head. I cannot find analogy, right? But you got the idea, right? So it's not, this description doesn't give us information, much information at the moment, about the life of this person in the country, of this mass, left mass. And of course, we also doesn't know exactly the life of the right mass. So we introduce this fancy point, okay, maybe not so fancy center of mass, very useful point, right? But again, it doesn't give us information about the life of actual people in the system, particles in the system, right? So now let's sort of add additional part to this problem, and let's calculate, for example, velocity of this mass right after the impact, and velocity of this mass, for example, right after the impact, And of course, the transition is not that complicated. Once you know this and that, you should be able to describe life of ordinary people, right, in the system. Okay, so now let me calculate velocity of this mass first, of the left mass, leftist, and we have rightist, right? Rightist is what? Republicans, right? And leftist, Democrats, so something like this. So I will put a new bullet over here, right? So let's look at life of ordinary people. So left mass. Okay, let me write leftist, left mass. Of course, the velocity of this mass will have two components. So first, translational motion of the center of mass gives us some contribution. And also at the same time, since we have rotational motion of the whole system about the center of mass, so of course there will be some tangential velocity associated or connected with this rotational motion. Tangential velocity, of course, of the mass. Right? So let's add those two contributions. So, which way I wrote v left. V vector left equals v center of mass, velocity of the center of mass, and then plus cross product of omega and r position vector of the left mass. Omega cross r with the subscript L. L stands for left. Yeah, we're discussing left one. Right? Okay, so now let's write carefully this vector equation. So VCM, yeah, that's this. And I think I will write immediately vector form in terms of f times y hat. F dt over 2m y hat, right? So that's velocity, and now v omega cross r plus. Okay, omega. I don't want to write this factor for now. Let me just use absolute value of omega, right? So will be omega minus z direction. So it will be minus omega z hat crossed with RL. RL, what is RL? Again, it's a position, so this will be RL, right? Pointing in the negative x direction. It defines position. It's position vector. Mass m on the left side of the origin, so vector is negative. So it will be what? Minus, and the absolute value, of course, b. Absolute value is b. So minus b x hat, right? Okay. What's the cross product? So x, y, z. So it's a cyclic permutations, x, z. No, z cross x, so it will be y. All right. Z cross x, it's a y. And we have two minus, so plus, so we'll get plus y direction. So it will be f delta t over 2m y hat plus, and now I will write explicitly omega. Right, so omega, where is my omega here? F delta t over 2mb, right, times b, and z direction. Oh, not z direction. As I said, z cross x, it's a y hat. Right? Okay, so we have two components, two contributions in the same direction. Nice. Right. Constructive work. And of course, b gets canceled. And we have f delta t divided by m. F delta t divided by m y hat. So that's the velocity of the left mass. Right. So now let's do the same for the right mass. Right. So now V right. Again, it will be the same in a vector form. A contribution from the velocity of the center of mass plus tangential velocity of the rotational motion. R sub R, position vector of the right mass. Right. And you know what will be the answer, right? So pretty much it will be exactly the same, but now R sub R, it's a Bx without minus. Right? So that minus is not going to be cancelled by anything. So as a result, over here we're going to have minus. Right? It will be minus, and we will have exactly the same terms. Here, these two terms, they just exactly the same sort of in value, they just added each other. But in this case, we're going to have minus, and we have this term minus exactly the same term. So over here, we will end up with 0. I just decided to skip it, because it will be exactly the same, except for here we'll have here plus bx hat. So it looks like, look, at initial moment of time, right after the impact, where is the whole linear momentum? You see at the very beginning, I told you, right? So this amount of linear momentum was dumped into the system through this force, right? So F delta T. And the question is, where is that linear momentum? Where is the whole linear momentum? Look, right mass has nothing, no linear momentum. And the left mass, so if you take this m times v, it's a linear momentum of the left mass, F times delta T. So pretty much the whole momentum is in the left mass, in the leftist, right? Right. So Democrats has all the linear momentum, all the momentum, right? And rightists, right, has nothing. But of course, as time would go by, right, so of course, at a certain moment of time, of course, the right mass will start getting everything, right? So just balancing. But at the initial moment of time, right after the impact, so the whole, all this linear momentum is in the left mass. Right mass has nothing. Because, all right, so translational motion up, but rotational motion is down. So basically they balance each other out, completely giving us nothing. Okay, so that's what I wanted to discuss about this problem. And as I said, very similar will be in your homework, but force will be applied at the angle. Right. Okay, so now, okay, so this should be enough in order to finish the homework. Right. So I'm giving you a week in order to finish it. Should be more than enough. Okay, so now we need to move to the next chapter, and but first we need to understand where we are and what we need. What do we need now? So as I said, we laid down the foundation, right? And in that foundation, in order to describe motion of any system, classical mechanical system, right, Newton's second law is enough, right? So grab Newton's second law, right? Of course, you can find the reference frame inertial using first Newton's second, using the Newton's first law, right? So pretty much at this point, we have everything that we need in order to describe motion of any system, classical mechanical system. It's just a question of doing. Of course, it can be ridiculously painful, right? Using Newton's second law, right, to describe some system, right? But it's doable. Theoretically, it's doable. So we have all needed and all necessary tools. So at this point, pretty much we can say, okay, we're expert, we know everything, right? You can buy yourself a T-shirt, life is good, and enjoy your life, right? So what usually a natural response of any brain, of any normal human being at the point where you feel comfortable in a certain field, in a certain area? Since your brain never stops thinking, analyzing, right? And still, since the brain is somewhat lazy, right? Of course, it will start searching for options how we can simplify our life. Actually, brain is very, very good at that, right? In a search for simplification, because it doesn't want to spend energy, because mental activities requires tons amount of energy, right? So it's just natural ability of the brain. So at this point, at this moment, we are sort of at the point where we are comfortable with this procedure, right? Using Newton's second law, but the brain starts searching for simplifications, right? How can we simplify our life? Is it possible, right? And so now we need to move into a different approach which can be used to describe the system. Again, do we have to go to that approach? Not completely necessary, right? So we have everything that we need. But we can make our life easier if we introduce what? Scalar quantities. So basically, instead of using forces, right, all these vector quantities, which is straightforward but very tedious, and even sometimes boring to use, depressing to use, right? Especially if you have many forces acting, right? Adding them all up, right? It can be painful. So the question is it possible to replace those vector quantities with scalar quantities, right? And then life can be easier, might be easier. So pretty much now we need to start developing a new approach, scalar approach, which should be easier for us. Again, as I said, it's not completely necessary. If you hate a scalar approach, go ahead. You have Newton's second law. Of course, sometimes it can be like a masochism, right? Because energy approach can be, okay, scalar approach can be easier, right? Okay, so now, starting from today, we're going to spend lots of time developing this new energy tool, completely new set of tools, right? Energy box of tools. Okay, so now I can, what's the trouble? Probably one of the major troubles using energy approach. That there are many forms of energies. Potential, kinetic, of course we will introduce them all. Potential, kinetic, right, thermal, right? And all this energy tends to flow. This energy can go there, this energy can go here, right? That go over there, right? So you have to keep track of all these energies, right? Hey, where are you going? And the energy is flowing, right? So that's one of the major troubles, so that there are so many different forms of energies, and you need to keep track of all of them. It's one of the maybe major or not so major drawbacks of this approach. Okay, so now let's start developing this. Okay, it's a chapter 4. Basically, it's an alternative approach. Again, if you hate it, you can still use Newton's second law, no troubles. Right, so chapter 4, energy. Right. And where should we start? Again, we are developing this alternative approach to address problems, but it doesn't mean that we change the foundation. Still, the foundation is exactly the same, basically. So it means that we have to start still from the same foundation, from the Newton's second law, in an attempt to find something which can be used instead of, for example, Newton's second law. But still, the foundation is still the same, right? All these searches for simplifications don't change our foundation. We're still searching for something new, easier, but still starting from the same foundation. Right? It means that we need to start from the Newton's second law in an attempt to build or develop some substitute. Like instead of using sugar, you can use whatever that crap is used, right? Instead of sugar, right? So the same here. So we'll start with the Newton's second law. Single particle travels along some trajectory. Right. All right, so let me write. So we need to start from the same foundation. The same foundation. It's very important. So we're not changing our foundation. Right. And so let's assume that we have some point mass, right, m, which travels, let's say, along this trajectory, exposed to some force. Yes, let's say, so there's some force acting on the system, right? On the mass, not the system, on the mass. Right? Because Newton's second law for a single particle. And so, according to our foundation, right, so Newton's second law, in its original form for point mass, so we can write mr double dot equals to the force, right? So that's the foundation, and now we need to somehow develop scalar quantities out of that. Right, so which mathematical tool can lead us from vector quantities to scalar quantities? You all know that. We all know that. I think it's the only one. I'm thinking, right, so I cannot come up with something else. It's a scalar product. Scalar product, what inputs? We have two vectors. As an output, we have a scalar number, right? So let's use scalar product in order to sort of, in an attempt to dump our vectors. Right, so dot it, let me dot it with r dot. Right. So a scalar product can dump vectors. That's why multiplying both sides of the equation, dotting with r dot. Right? Okay, so as a result, we will end up, of course, with m r dot dot r double dot. I change order, but scalar product, who cares, right? Equals to f dot, oops, with r dot. Okay. Now let me make this equation look uglier. I'm going to do it this way. So I will take m. Okay, it's time to change marker, but class is almost over. So I will do it this way: r dot dot r dot, and now I'm going to dot a lot. Then I will add exactly the same thing: r double dot dot r dot, right? And so that I can avoid your screaming, I will put 1/2. So it's exactly the same, right? And equals to f dot r dot. And of course, now this can be written as d over dt m over 2 r dot squared. Look, if you, okay, m over 2 goes outside, and then if you differentiate this, so first you will differentiate the first r dot, you will get r double dot, dot with r dot, and then the second, of course, it will be exactly the same, but with the second r dot. So you will end up with exactly the same. And equals to f dot r dot. Wait, hold it. No, it's fine. Yeah, that's correct. Started doubting myself slightly. Okay, so first of all, we're getting, you know what, let me dump dt. Let me dump dt. Here dt and here dt, right? So, wrong color. So I will get d m, and also instead of r dot, I will use v squared, v over 2 equals to f dot dr. Right. Okay, and now, so we massaged, basically sort of deep Swedish massage to this Newton's second law, and we ended up with this. So first of all, this new construction appeared, mv squared over 2, which we've never seen in this course. You remember, we're developing theoretical, developing this classical mechanics castle, right? Using theoretical approach, starting with the foundation. And we've never seen this quantity before in this course. So something new, and it looks like it will be useful in this new approach. Let's just give it a cool name. Kinetic energy, energy of motion. Right. So now we can introduce, so let's introduce kinetic energy. And again, the meaning, it's energy of motion, right? So T, 3 lines by definition. I think we use T in this course, right? Yeah, because some books use K, right? So sometimes I'm confused which one. mv squared over 2. So kinetic energy. Energy of motion, right? And okay, let me write next line, and then we'll continue from the next class. And then we'll continue in the next class. So what's left over here, of course, now it's dt equals to f dot dr. Okay, so it looks like kinetic energy changes when this happens, right? F dotted with dr. And again, it's something which we've never seen before. It looks like it will be crucial in our description. Again, let's give it a cool name. Work done by the force over this displacement, infinitesimally small displacement dr. Okay, I can show that this, for example, infinitesimally small displacement dr, right? So we can write, again, introduce a new quantity with a cool name, work. Right. So W, by definition, F dot dr, work done by F, right? And of course we can frame it because it's a crucial quantity in a new set of tools, in a new toolbox. And as a result, we're getting that change in the kinetic energy equals to the work done by the force. And this is extremely crucial. Let me frame it twice. Why? Because in the previous approach, right, Newton's second law was used to describe motion of any system. Now, that substitute, which can be used instead of Newton's second law in the energy approach, it's a work kinetic energy principle. So pretty much now, if you want to describe motion of any system using this energy approach, that's your tool. Work kinetic energy principle, of course. So work kinetic energy theorem. Conservation of mechanical energy follows from here. If forces are nice, in a couple of classes we will introduce nice forces, right, and the potential energy and so on. But this, since deriving this, we haven't applied anything except for some mathematical ideas, right? So we haven't applied basically anything, and this doesn't have any restrictions as Newton's second law. Universal, no restrictions, any forces, any systems. Work kinetic energy principle instead of Newton's second law. Okay, so sorry for holding you for extra 5 minutes, right? Because I wanted to emphasize. So now we found Newton's second law substitute in this new approach. Work kinetic energy principle. Okay, so let's call it a day over here, right? And then we will continue from this point tomorrow. Or not tomorrow, Thursday. So if you have questions, go ahead. Work kinetic energy theorem. Okay, theorem sounds cooler, but I usually use principle. Right. And maybe let me write also, so Newton's second law substitute. And of course, in this energy approach. All right, so again, as I said, if you have questions, ask. So from this point, we're going to spend quite some time on this chapter 4. It's a big one. So first, we will just develop all these tools, which we need in order to describe system using this energy approach. And then once we finished developing these tools, we will start applying all that for one-dimensional systems. The simplest possible, right? And still, one-dimensional systems can be can be complicated, right? And after that, basically, yeah, we will move to oscillations, right? So then start preparing ourselves to the Lagrangian formula.